So I know now that I've been doing these for a little bit, some of you guys realize I'm kind of a ham, right, for this kind of stuff. So I was on a walk today with my wife, and I was kind of thinking to myself, I was like, oh, I just came up with a little bit of a little rhyme for this intro. But I'm kind of embarrassed to do it. My stomach kind of hurts, so I'm gonna see if I can do this right now. See if it works. Okay, here we go. Deep breath. Okay. Let's talk about P and V. Let's talk about NRT. Let's talk about ideal gas laws. It's too late. I'm doing it. All right, guys. So, what are we talking about today? We're going to be talking about the ideal gas equation. So, we're basically taking everything that we've been talking about for the last few days, and we're going to kind of combine everything around. Now, mind you, is only going to work out. This is only going to work out is if all these things are constant and nothing's changing. The truth of the matter is, and we'll discuss this later on, is that we're going to come to the realization that not all gases work out in this ideal way. We'll talk about that later on. It has to do with intermolecular forces and whatnot. But anyways, so what we've seen so far is that when volume is directly proportional to the inverse of pressure, right? That's Boyle's law. Volume is proportional to temperature, which is Charles' law. And we also learned that volume is also proportional to moles, which is Avogadro's law. So when we take all those, we come up to the understanding that when you have volume, it is proportional to moles times temperature divided by the pressure of a system, right? Given that it's an ideal gas law. Now, because not everything works out perfectly, we have this constant that we can use, and we call this the ideal gas constant, otherwise known as R. I'll tell you what that is in just a minute. But when we put that all together, we get this nice, easy equation that we can use that some people lovingly call PIV, right? PV equals nRT, or pressure times volumes equals moles times the gas constant times temperature. Now, there's a couple things you got to understand when we're doing this. First and foremost, your temperature has to be in Kelvin, your volume has to be in liters, and your pressure has to be in ATMs in order for this equation to work. So you have to make sure if you're ever given a problem and those conversions aren't there, that you do those conversions so that way you actually have it. So there's our ideal gas equation, PIV, PV equals nRT. Anytime you have a gas problem, I guarantee you, when you see it on paper, automatically you're going to jump to that equation right there, just because that's how we do these things. Okay, so this is just a little bit more on this, just to kind of break it down, and this is kind of what we talked about earlier. But the one thing I want you guys to focus on is the R, right? The gas constant, universal gas constant. The universal gas constant, now you should write this down somewhere because it's really, really important. Most of the time you're given it, but it's good to just know it. It's 0.08206 liters times ATMs, or pressure, divided by moles times Kelvin. Those are the units for that, but that is the universal gas constant. That's what this R means right here. Remember that P is pressure, V is volume, N is equal to moles, and T is temperature in Kelvin. R is the universal gas constant. Okay, so let's get to our first example here. An automobile tire at 23 degrees Celsius, think about that, with an internal volume of 25.0 liters is filled with air to a total pressure of about 3.18 ATMs, and it wants to determine the moles of air in the tire. So the first thing that I'm going to do, right, is I'm going to write down my equation. I'm going to put it up here because I'm going to kind of move things around. PV equals nRT. Now, since I know this is an ideal gas equation or ideal gas problem, I'm going to look at what they're asking me. I'm going to look at what they're telling me, right? So first and foremost, the information that they're giving me, right, is they give me temperature, they give me volume, they give me pressure. So the only thing they're really not giving me, because this is a known, is they're not giving me the moles of the problem. So I'm going to manipulate my equation so my equation is equal to moles, right? So I know that I have to get rid of the constant and temperature, and I get this brand new equation that is this: N equals PV over RT. Pressure times volume divided by the universal gas constant times temperature is going to give me my moles for this equation. Okay, so what am I going to do now? So now what I'm going to do is I'm going to punch in all my values, right? So that way I can figure out what the moles are. So I'm just going to plug and chug now, okay? So I know I've used that word plug and chug, and I think this is actually where I got it from. I think I remember hearing a professor a long time ago say, no, we're just going to plug and chug. So now that's what we're going to do. We're going to plug and chug. So we get N, right? So the pressure for this problem, which is already ATMs for us, is 3.18. So I'm going to put 3.18, right? And this is ATMs, times my volume, which is already in liters for me, which is 25.0 liters, right, divided by my universal gas constant, which is 0.08206, right, times my temperature, which is unfortunately, most of the time when you get temperature, it's not going to be in Kelvin, it's going to be in Celsius. So just know that you always have to do that conversion most of the time if it's given to you in Celsius. Now remember that our conversion to convert Celsius to Kelvin is 23, and you just add 273 to it. Now, just because I'm in a hurry, I'm going to put it just in my equation just like that. So I'm going to put 23 plus 273. Now, if you want to get more specific, once again, it's 0.15, but we'll just put it like that. Pop it into my calculator, and when I do that, I get a grand total of 3.27 mole of whatever air is in there. Maybe it's like a combination of nitrogen gas or something like that. Who knows, right? It's a bunch of different things. So anyway, so when we have at 23 degrees Celsius, as long as this is an ideal gas, right, and it's 25.0 liters at 3.18 ATMs, the total number of moles that we have of air in there are 3.27. Now, if we knew the identity of that gas, we could actually figure out the actual mass of it. We just have to multiply the moles times the molar mass, and that would actually give it to us. All right, so here's another example, and this problem is a little bit different than the last one we just had. So what is the pressure in a 304.0 liter tank that consists of 5.670 kilograms of helium at 25 degrees Celsius? Now, once again, this is an ideal gas law problem, right? So we have PV equals nRT, right? Now let's look and see what we got, okay? So first and foremost, we don't have pressure because that's what they want to know, right? So we're going to manipulate this equation so that way it is equal to pressure. So I'm going to say pressure is equal to, I'm going to divide volume from both sides. Pressure is equal to moles times the universal gas constant times temperature, all divided by volume, okay? Because that's the only thing, pressure is the only thing that we don't have. Now we're going to look at the problem and see what we got. Well, do they give us temperature? Yes, they do. They tell us it's 25 degrees Celsius. We have to convert that obviously to Kelvin, right? Do they give us the volume? Yes, they do. It's 304.0, right? Do they give us the, do they have to give us the universal gas constant? No, because we know what it is. We know that it's 0.08206. However, what they don't give us is they don't give us the moles of helium that we have, but they do give us a mass. So we have to do a little conversion here. We have to convert grams to moles. Now in this situation we have kilograms. So the very first thing I'm going to do is I'm going to convert kilograms to grams, right? So I know that for every, let's just show you. I'm going to do this in one like straight problem just to show you guys something. So we have 5.670 kilograms of helium, of get it? Because it's funny. Oh, stop. All right, of helium, right? And we're going to convert it to grams of helium. Now, I know that for every 1 gram or 1 kilogram, I have 1,000 grams. Okay? Now that's going to convert out. Grams are going to be gone. My next thing is I'm going to convert it now to moles of helium. Okay? So in order for me to convert to moles of helium, I know that my conversion factor is molar mass. So I'm going to get rid of grams. I'm going to put grams down here. I'm going to put moles up here. For every 1 mole of helium, I have 4.003 grams. Okay? Start canceling out my units, and I'm left with moles of helium. When I do all that stuff, I get 1.416 times 10 to the third moles of helium, which makes sense. I mean, think about it. You have, 5.670 kilograms. That's a lot of gas, like a lot of gas, right? So you'd expect to have a great number of moles in there. So this is how much we have. I'm going to put this over here on the top so I don't forget it. 1.416 times 10 to the third moles of helium. I'm going to erase all this other stuff out of here, as long as it'll let me, which is it is not. And like magic, it's gone. All right, so now we have everything we need, right? We have our moles, we have our pressure, we have our volume, we have our temperature, and we have our universal gas constant. Now, when we plug this in, I'm going to leave all my units intact, just so you can see them kind of canceling out. So my pressure is going to be equal to, I'm going to write this a little bit bigger, 1.416 times 10 to the third moles times, I'm going to do this in different colors, so I'm going to do this in green, right? So if you're red, green colorblind, I'm sorry. I really do apologize. I hope you're not. If you are, let me know. 0.08206, and the units for the universal gas law are liters times ATMs, which is pressure, divided by moles times K for Kelvin. I'll close that all in the parentheses. And then after that, we have 25 degrees Celsius. Remember, converted to Kelvin, so we're going to add 273 to it. When you do that, you get 298. Now, and the other problem, you guys kind of saw that I did this before, right? Or you can do it during. It doesn't matter when you convert it, just convert it at some point, okay? Well, convert it before you start multiplying things around. If not, it's going to mess everything up. So I just did it before. When I used to do this all the time, I'd always do it before. So then I get 298 Kelvin. I'm going to divide all of this stuff by my volume, which in this case, I'm going to do this purple color, purple, 304.0 Kelvin, okay? 304, oh, did I say Kelvin? My mistake. I meant liters. My bad. All right, so now what I'm going to do is I'm actually going to go through this, and I'm going to cancel out all of these units just to show you guys, right, what I'm talking about. So we have moles right here. I'm going to do it like a black color. We have moles right here and moles right there, and they're on opposite sides, so I'm going to cancel those out. Those are gone, right? I have liters over liters, so those are going to cancel out just like that, right? I have Kelvin and Kelvin on opposite sides, so Kelvins cancel out. Therefore, the only thing I have left is ATMs, which is what I want. That's the last unit that I have left, so I know that I have pressure, okay? So once I multiply all this stuff out, I get pressure is equal to about 114 ATMs. So when I have a 304 liter tank that contains 5.670 kilograms of helium at 25 degrees Celsius, right, then the pressure has to be 114 ATMs of gas. That's a lot of pressure, right? Like just for some frame of reference, I think, if I'm not mistaken, I'll have to look it up. I have to look it up, see what the standard pressure is for a tire or something like that. Okay, but there's a lot of pressure there. Okay, just a lot of pressure. Okay, so here's the problem that I want you guys to work on. Now, this problem is a little bit more complicated than the last two, so here I want you guys to pause your video, not just yet. I'll tell you when to pause it. Right, pause it and then answer this question. So here's the question. At what temperature in degrees Celsius, so remember the final temperature has to be in degrees Celsius, does 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 ATM occupy a volume of 293 milliliters at a pressure of 1.40 ATMs? Now, before we start, understand one thing. This problem is a little bit different than what we've been talking about, but it's still kind of the same thing, right? This is still a combination of Boyle's and Charles' law, right, put together, except for one key difference, right? We don't account for Avogadro's law because here moles are constant, okay? So you can just kind of get moles out of the equation here. Just pretend like it doesn't even exist in this part, all right? And remember, you don't have one system now, you have two systems, okay? Two systems with their own pressure, their own volume, and their own temperature, okay? So do what you will, see if you guys can figure this out. This is a bit of a challenge. So now you guys can pause your video, answer the question, and make sure you answer it in teams. If you're watching this video, you're not a part of my class, answer in the comment section below, all right? So here we have some more uses for the ideal gas law, and we can actually use the ideal gas law to find the density of gases. Well, let's figure out why we can do that. Well, first and foremost, if we divide both sides by the ideal gas equation by volume and by the universal gas constant and temperature, we get this new equation. Moles divided by volume is equal to pressure divided by the universal gas constant times temperature. Okay, well then also you have to understand this, right? That when we take moles times molecular mass, well, it gives us mass, right? That's simple stoichiometry. So we're combining this, and we get this brand new equation. And this is the equation that we get. We get mass divided by volume is equal to molar mass times pressure is equal to, or divided by the universal gas constant times temperature, okay? Well, if you have mass and volume, realistically what you got is density. So we have another derivation of the same equation here. Density is equal to, now because we know mass divided by volume is density, density is equal to the molar mass, right, the molecular mass of something times the pressure of something divided by the universal gas constant times the temperature in which that gas is found. If we have all that information, then technically we can find the density of a gas. How many particles are located within that object, right? So we have something we can use density. So there are a lot of different ways in which we can use the universal gas law to find unknowns. This is just another example of that. All right, so let's recap real fast. So here's how we recap. One needs to know only the molecular mass, the pressure, and the temperature to calculate the density of a gas. So as long as you know those three things, because one of those we already know because it's a constant, right? That's the universal gas constant. If you know the molecular mass of your object, if you know the pressure of your object, you know the temperature, and we all know the universal constant, you can find the density of that object, which then means we can also find the mass of whatever gas we're dealing with, right? Which becomes very, very important when you're trying to figure out stoichiometry, right? So this is an example of gases with stoichiometry. Also, if you know the mass, the volume, and the temperature, then you can also find the molar mass of your object as well. By that same reason, if you know the identity of your gas, then you can also find the mass of your gas as well, okay? Good stuff. All right, so what about problems like this, okay? So molar volume of an ideal gas law. So for 1 mole of an ideal gas at 0 degrees Celsius and 1 atm, the volume of a gas is 22.42 liters, or sometimes written as just 22.4, right? So we have these things called STP. So what that means, if it's an ideal gas, right, and you have 1 mole of the substance at 0 degrees Celsius, which is 273 Kelvin, and 1 atm, the volume of that ideal gas will always be 22.4 liters, no matter what, right? It's as long as it's a universal, as long as it's an ideal gas like nitrogen gas or oxygen or something like that. So we're going to cancel all these suckers out, and it shows us kind of going through all of that, right? And we get this. So when you ever see STP, what that means is standard temperature, standard pressure. Standard temperature or pressure are 0 degrees Celsius or 273 Kelvin and 1 atm. If it's, so therefore, the molar volume is 22.42 liters at STP. So at standard temperature and pressure, the molar volume of what you have is 22.42 liters, okay? So remember that. Standard STP, standard temperature and pressure, 0 Celsius, 1 atm. If you ever see that, that's what you have, okay? Which is what we have right here, right? So a sample of oxygen has a volume of 2.50 liters at STP, right? Standard temperature and pressure. How many grams of oxygen gas are present? Well, first and foremost, there are a couple of different ways in which we can solve this, but they're asking us for grams. So right now, as our equation set up, P equals, or PV equals nRT, there's no math anywhere here. Yeah, I know we kind of broke down the density equations and all that stuff, but there's a way we can figure out using this equation right here, okay? So we don't have mass on here, but we do have moles, right? And as long as we know the identity of our gas, we can use moles to then figure out mass of the object. So I'm going to reconfigure my equation here. I'm going to manipulate my equation so that way it's equal to moles. So I get this new equation, moles equals pressure times volume divided by universal gas constant times temperature. Now I simply just plug and chug and figure out what my answer is. So moles here, I'll write this a different color, equals, remember, it's at STP. So at STP, even though they only really give us the volume, at STP, our pressure is going to be 1.00 atms times my volume, which in this case is 2.50, divided by, don't forget, my universal gas constant, which doesn't change, is 0.08206 times standard temperature. Now remember, standard temperature is 0 degrees Celsius. Some of you guys are gonna be like, 0. No, don't do that, right? Or else it's not gonna work, right? You can't divide anything by 0. Okay? So what you should do instead is first convert it to Kelvin. Now remember, at standard temperature and pressure, temperature is 0 degrees Celsius, which means at Kelvin it is 273 Kelvin. Put that all in parentheses, put it in my calculator, bing, bang, boom, and I get 0.112 moles of oxygen gas. Now, they asked for this in grams, so I'm not quite done yet. So now I have to convert moles to grams. So I have 0.112 moles of oxygen gas divided by, or multiplied by, the molar mass, which in this case is 32.00 grams, right, over 1 mole of oxygen gas, okay, which equals, when I multiply it all out, cancel out my units, right, and I get 3.57 grams of oxygen gas. So what does that mean? That means at its standard temperature and pressure, when I occupy a volume of 2.50 liters, right, I have approximately 3.57 grams of oxygen gas, okay? So let's see if you figure out one of those. So here is another use of the ideal gas law, right? We can use the ideal gas law to know or to find the molar mass of an object. Now, most of the time, we're not going to be finding the molar mass, but it does allow us to use molar mass to find things like density, temperature, or even the pressure of a system, right, or of a gas. So what we have here is when we have molar mass is equal to the density times the universal gas constant times temperature, right, divided by pressure is going to give us grams per mole, which is molar mass, right? So we can use all the information that we have here to solve for molar mass. But in most cases, what we're going to see is that we're going to have a situation in which they're going to give us the identity of a gas, for example, fluorine gas, chlorine gas, different types of ideal gases. Then we can use that information to then solve things like density, things like temperature, and things like pressure for a given gas, as long as we know the identity and as long as you know at least two of those other things, because we'll always know the universal gas constant. So they're kind of canceling out units here, and you see that the only units that you're left with are grams per mole, which as we know is molar mass. So another wonderful use of the universal gas constant, which is what we have right there. Okay. Now, our second, I know you're getting 2 concept checks in one YouTube video. All right, so here is your next concept check. What I want you guys to do is I want you guys to find the density of fluorine gas at STP. All right, guys, good luck. Make sure you put these in teams, and if you're not a part of this class, put them in the comment section below. All right, guys, we'll talk to you guys later. Peace out.